Welcome to Silicon Labs ZigBee Concepts Training, Part 4. In this training module, we're going to discuss some more ZigBee concepts that revolve around common network activities. These include forming, joining, and building out the network. We assume that you have already watched the preceding parts of the ZigBee Concepts video series, or are familiar with concepts such as ZigBee node types, PAN IDs, extended PAN IDs, and addresses. Let's begin where the network begins, and that's about creating a network. When a ZigBee network starts, it all begins with the ZigBee coordinator, the ZC. This is shown in our diagram here. If you remember from the previous part of this video series, the ZC is represented by a thick red circle. The thin red circles are routers, and the thin blue circles are end devices. The coordinator begins by choosing a channel which would be one of the 2.4 GHz allocations designated 11 through 26. These represent channels with center frequency from 2.405 GHz all the way up to 2.480 GHz. Then the coordinator is responsible for choosing a unique 2-byte PAN ID as well as a unique 64-bit extended PAN ID. If you recall from our last presentation regarding PAN IDs, the short PAN ID is generally used to divide the network, but in case a conflict arises, the extended PAN ID is our backup scheme. Once the coordinator has chosen the channel, PAN ID, and extended PAN ID, the network grows by allowing more nodes, such as a router or an end device, to join through the existing coordinator. The basic idea here is that a device can't get into the network except through a node that is already in the network. The exception, of course, is the coordinator, who has this special property of being able to form the network without having to get permission from anyone. After the first router joins the coordinator after the network formation, future nodes can join the network through the coordinator or the new router. They cannot join through the end device because an end device doesn't have the ability to route. As the network grows, we start to form a tree-like structure that builds out from the coordinator, with the end devices generally being on the fringes of the network. From the perspective of joining a network, suppose that your device who wants to come into the network is embodied by this purple circle, neither red nor blue yet because it hasn't actually joined the network and doesn't have a node type yet. First of all, the device has to scan across all channels to decide what networks are available. Then it has to solicit router and coordinator nodes to determine what networks are there and which are available devices through which it can join. This process is called an active scan, an IEEE 802.15.4 MAC concept where we send a beacon request, which is a single hop broadcast that transcends all the PAN ID boundaries. Every device in every 15.4 network within range can hear this beacon request, and they are supposed to respond with some indication of their network, such as PAN ID, extended PAN ID, and stack feature set, and a Boolean parameter that says whether or not there's any joining allowed. This joining allowed property is done on a case-by-case basis for each node, so that it may be 2 nodes in the network available, but only one of these nodes is actually allowing new devices to enter. It's something like having multiple access points into a network where they can be enabled or disabled for accessibility to new devices at will. The other information that's not displayed in the diagram here is that there is also information from the router or coordinator about its ability to sustain additional end devices. So if you are an end device wanting to join the network, a potential parent might say it could let you into the network if you are a router, but because it can't support any more end devices, it can't let you in. This allows the end device to rule out that node is a potential parent. In this diagram, in action number 1, we see a large arrow soliciting devices with its beacon request, and the individual indications are beacons coming back. Whichever beaconing device is heard best becomes the parent node of the joining device. Once this is chosen, the joining device submits an association request to the chosen node from the chosen network. This is action number 2, the arrow going across to the chosen device. At this point, there is no security authentication. It's simply that someone submits a join request to a node and it's permitting joining, and it is able to accept a new device. Then it should create and send a random address to the joining device, and now the new device is successfully associated into the network. This is shown in action number 3. This process of association is really a very simple one-to-one device process and doesn't involve contact with other nodes. After the association takes place, there is a security authentication step with the Trust Center device to complete the story. However, we will not go into that in this video. Now, let's take a look at our Ember ZNet implementation that corresponds to the activity steps we just talked about. For a node that's already in the network, typically it calls the Ember permit joining function with a given duration as a number of seconds that says this device is going to allow new devices to associate through it into the network in this many seconds. If you are the device that's trying to come into the network, you need to find a node that has recently started permit joining action, so it's currently permitting new devices. We have a utility function called Ember scan for joinable network, and this function takes the mask of channels and a desired extended PAN ID. So, if your new device already knows exactly which network it wants to join, it can restrict the results by an extended PAN ID criteria. If it doesn't know that, it can just pass all zeros in this field, and the search will return results for all available networks. Next, the search results will come up in the Joinable Network Found handler. This application will mediate the results and decide which of those networks it's interested in possibly joining. Then, the application is going to call Ember Join Network on one of those networks. The networks are embodied in a network parameter structure. You pass the pointer to this structure and also the node type. The stack has no idea of the node type of this new device until this point. Assuming all goes well, you should get some indication that the join has succeeded. Observe that in all the criteria that you have so far for selecting the network are the PAN ID, extended PAN ID, and a somewhat arbitrary channel value. This may not be enough information to decide whether the network is the right one. So, once you have joined the network, if you find that it's not the right one, either by yourself or through another device, such as an installer, you will have to leave or be taken out of the network, find the next joinable network, and go through the join process again. It's not uncommon that you're going to go through this iterative process until you find the right one. Besides the typical joining process, other network activities commonly occur based on the device type or the network state the device is in. If you are the coordinator, you will call Ember Form Network to form a new PAN before the devices can join. Another common network activity is restoring a network. This is possible because the Ember ZNet stack stores network information including security criteria, PAN ID, channel, node type, and network address in non-volatile memory. This is useful because if a device were to reset unexpectedly, you would want to retain all your network settings and be able to recall that information to come up right where you left off and not have to recommission the entire network simply because of a brownout. If you use our Ember application framework or sample applications based on the application framework, Ember network init function is called by default right after initializing the stack, so that the device, as they come up from reset, will try to check if there's a valid network information already stored from the last run. If there is, that information will be restored and the node can get back on the same network that it was before. This is usually straightforward for a coordinator or a router. For an end device, however, it may not be so simple if it can't find its parent any longer after a reset. If you have an end device, you must have a valid parent. If you call Ember network init as an end device, it's possible to get to a state where you are technically associated to the network, but you don't have a parent. At that point, you really have to start a process to rejoin the network. A rejoin is necessary not only for an end device to find a new parent, but also for routers who have lost connection to the rest of the network. For instance, the network has changed channel or PAN ID, but somehow you missed it. Whenever the application wants, you can call Ember find and rejoin network. Because the extended PAN ID never changes in the lifetime of a network, even if the channel or PAN ID has changed, the rejoin works because the device can look for a network with the extended PAN ID that it knows about. Because you already have been accepted into the network once, and this is a rejoin, you ignore the permit joining state for this purpose. Again, the rejoin process is recommended and typically used for an end device that has lost connection to its parent. This concludes our discussions on network activities. You have seen how networks are formed, how devices join and rejoin the network, and how to resume a place in the network, and the Ember ZNet API calls you would use for typical network activities. For more information on these concepts, please refer to UG 103.2 Ember Application Development Fundamentals, ZigBee. Or, for more advanced programming, please refer to UG 105. Please also see other parts of the ZigBee Concepts video for a series comprehensive overview of ZigBee Concepts. Thank you for watching this video course. We hope you learned something useful about ZigBee Concepts.